Hi everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. In this video, we're going to answer the question, can we partially test our instruments? So we're going to talk about over-identification tests, Sargan Hansen test. When we have one instrument, one endogenous variable, no direct test can happen. So what will happen when we have more instruments than endogenous variables? Surprisingly, that gives us something that we didn't have before, a way to partially evaluate our IV strategy. Okay, so just identified versus over identified. You have endogenous variables, 1, 1, instrumental variables in the just identified one, you have exactly 1, you have here more than 1. So actually, let's say 2 or more. Then in the just identified one, you have exactly enough information to estimate your beta hat, which in the cases where you use the IV, we'll call it beta IV instead of beta OLS. In the over-identified, you have 2 or more instrumental variables, so you have more instruments than strictly needed. Okay, so you have surplus information here. And it's exactly that surplus information that makes this test possible. So the degree of over-identification is equal to the number of instruments minus the number of endogenous variables. With 2 instruments and 1 endogenous variable, you have 1 degree of over-identification and 1 testable restriction. Okay, so keep in mind, degree of over-identification is number of instruments minus the number of endogenous variables. Okay? With 1 instrument, there is only 1 way to estimate the effect, so we have no choice but to use it and no way to check it. With 2 instruments, we have 2 independent sources of clean variation in X. Each instrument tells its own story about the causal effect. If both instruments are valid, if both satisfy the exclusion restriction, they should be pointing toward the same underlying beta 1. That's the key idea here, okay? So let's add the ifs as well. If both instruments are relevant, and if both satisfy the exclusion restriction. Now imagine instrument 1 suggests that beta hat is equal to 2.0. Okay, and also suppose that instrument 2, you've got beta hat suggests that it's actually 2.1. So when you use instrument 1, you get the beta 2.0. When you use instrument 2, you have beta hat 2.1. Now, these are not identical, but are still very close. So both instruments are telling a compatible story, which is reassuring. Now, imagine the case where your beta 1 hat is the 2.0, but in another case, with the second instrument, your beta hat actually is 10.0. Now, in this case, something is seriously wrong in here, right? Because 2 valid instruments should not disagree to that kind of degree. One of them, or both, may be violating the exclusion restriction in here. And the intuition is quite simple. Valid instruments are all measuring the same causal effect through different channels. If they give wildly different answers, at least one channel must be contaminated. If all instruments are valid, they should all point toward the same underlying causal effect. Not exactly identical, Sampling variation means that estimates will differ slightly, okay? So remember, there's always sampling variation. But the differences should be small enough to be explained by chance. Now, the Sargan Hansen test formalizes this intuition. It asks, are the differences between instruments too large to be a random? And what the test actually asks in here is basically, are the instruments collectively consistent with the model? Or more intuitively, are the instruments telling compatible stories about the beta 1? If yes, the test gives you supporting evidence for your IV strategy. If no, something in your instrument set is problematic. The test statistic for this is also called the J statistic. Okay. Under the null hypothesis that all instruments are valid, okay, it will follow a chi-square distribution with degrees of freedom equal to the number of over-identifying restrictions, which, as we said earlier, it's the number of instruments minus the number of endogenous variables that you have in a model. The Sargan Hansen test, keep in mind, does not prove, okay? So it doesn't prove it, your exclusion restriction. It's not a validity proof, okay? It's just a consistency check. Many papers report passing the Sargan Hansen test as evidence of instrument validity. Technically, it's only evidence of instrument consistency, all right? So this distinction matters quite a bit, and careful referees, as we mentioned earlier in the previous video, you need to be a referee, will notice that you cannot conflate the two of them, okay? Now, the null hypothesis, so all instruments satisfy the exclusion restriction or that they are all valid. The alternative is usually that at least one IV violates exclusion restriction. And keep in mind from the previous video as well that we use interchangeably exclusion validity. As always, with hypothesis testing, you're trying to reject the null. If we can't reject, that's good news for instruments. If we do reject, something is wrong with at least one of them. So don't worry if you fail to reject the null hypothesis. In fact, if you have come up with a good instrument, you should be happy that you failed to reject the null hypothesis. Most of the times, you will use the p-value, and as usual, large p-values will fail to reject the null hypothesis. The instrument will appear consistent with each other, which is good news, supports evidence for your IV strategy. When you reject, you should know something is wrong. But unfortunately, the test will not tell you which instrument is the problem. And that requires economic reasoning, not more statistics. So a common response to rejection is to basically drop one instrument and then rerun the test, but this can also become data mining. So you should have a very strong theoretical reason for which instrument you should be dropping and not just drop whichever that makes your test pass. There is a critical limitation, and suppose that instrument A is invalid, while instrumental variable B also invalid. But instrument A is invalid and it violates the exclusion restriction. B also in exactly the same way. Both instruments in here are broken, and they are broken in the same direction. So in the same way, let me write here. They still agree with each other. The test will see consistency and it will fail to detect the problem. Okay, so the Sargan test can only detect inconsistency between instruments. So it cannot detect if all instruments fail in the same way, because basically it's going to notice that consistency in failing in the same way. This is why the test is called the test of over-identifying restrictions, so not a test of validity. If your entire instrument set is contaminated by the same omitted variable, then the test will pass even though every instrument is actually invalid. Suppose two witnesses describe the same event, so you can make the analogy with that. If their stories completely disagree, you know that something is clearly wrong. At least one of them must be mistaken. But if their stories agree, that means that's reassuring. It's consistent. They are both telling the truth. But the agreement in here doesn't prove that they are actually telling the truth, because they could have coordinated their stories. They could have made the same honest mistake. So the Sargan Hansen test is exactly like this. Consistency is necessary, but ultimately not sufficient for validity. The Sargan Hansen test checks whether multiple instruments tell the consistent stories about beta 1. Passing is reassuring, but not proof of validity. So you should always be very aware. You could fail all the time in the same way. In the next video, we'll stack back and bring all of the stuff that we've learned so far together in terms of the IV before we move into estimation. So stay tuned, and I'll see you in the next video.